Welcome everyone. In this lecture, we will be learning about the boundary conditions for electromagnetic wave. In many cases, electromagnetic wave can be traveled from one medium to other medium. For example, the light wave travels from the sun to the earth, is propagated to many different medium like ozone layer, nitrogen layer, free space, and so on. Maxwell's equation for any particular medium. So in this lecture, we will be discussing about what happens if electromagnetic wave propagate from medium 1 to medium 2. Two different medium, different electric and magnetic features. We can write the Maxwell's equation for medium 1 and for medium 2. But what will happen at the boundary surface? So the Maxwell's equation are still valid at the boundary 2. The electromagnetic signal may be continuous or discontinuous at the boundary, but the Maxwell's equation still will hold there. We will be discussing how to write the Maxwell's equation at the boundary. So the Maxwell's equation at the boundary of two medium is called the boundary condition. So we are going to drive the boundary condition at the interface of two medium using the Maxwell's equation. Usually choose the integral form of Maxwell's equation to drive these boundary conditions. So look at the expressions here. The first four expressions are for the boundary conditions for a dielectric-dielectric interface. So if we have two different dielectric mediums meet at a particular point on that boundary or interface, we can obtain these four equations or special Maxwell's equations are called the boundary conditions. So in first expression says that the difference in electrical field, the difference of tangential component of the electric field is equal to 0. And the second expression says the difference of tangential components of magnetic field is equal to the surface current density. Third expression says the normal component of electric flux density is equal to the charge density on the surface. And the fourth expression says the magnetic flux density, the difference of normal component of magnetic flux density is equal to 0. So from these expressions, you can easily conclude that the tangential components for two mediums will be same at the boundary, and also the normal component of magnetic flux density will be same at the boundary. So electric field, tangential component of the electric field is continuous, and the normal component for magnetic flux density is continuous. So in both medium, the tangential component of electric field and the normal component of magnetic flux will be same. And also the tangential component of magnetic field and the normal component of electric flux are discontinuous. If we have a surface current density available on the boundary surface, and if the surface charge density is present on the boundary surface, but if there is no surface current or surface charge, then the tangential component of magnetic field and the normal component of electric flux will also be continuous. The second set of expressions, the other set of expressions that also consists of 4 different equations indicates the boundary condition for perfect conductor and dielectric interface. So if the electric signal transmit from dielectric to a perfect conductor, you will get these 4 boundary conditions. So these 4 boundary conditions can be derived from the above 4 equations, because as you know, inside the perfect conductor there will be no electric field, because for perfect conductor the sigma conductivity is very high. So if the conductivity is very high, it will produce the electric field 0. It will dissipate all the electric fields, and electric fields will be 0 inside the conductor. Similarly, magnetic field will 0 inside conductor, electric flux and magnetic flux all will be 0 inside the conductor. So if you have a solid conductor, thick solid conductor, at the center of the conductor all the electric and magnetic field will be 0. So if the electric magnetic field parameters are 0, then in the above dielectric boundary equations you can substitute E2 with and H2, D2 and B2 with 0. So if you substitute the electric and magnetic field components are 0 in the first set of expressions, you can easily come up with the second set of equations. Just only we drop the suffix 1. So E1 is changed to E. E is the electric field coming from dielectric medium, and H is the magnetic field for the dielectric medium. D and B are the electric flux and magnetic flux respectively coming from the medium, dielectric medium. But the E2, H2, D2 and B2 are 0 inside the conductor. So therefore we get the boundary conditions for dielectric and good conductor or perfect conductor interface. So that are E cross AN, normal component, so electric field tangential component will be 0, and the magnetic field tangential component will be equal to the surface current. So the magnetic field can produce a current on the surface of the conductor, and D dot AN, that normal component electric flux, also produce a surface charge. So electromagnetic wave traveling from the dielectric could induce a surface charge on the conductor surface, conductor dielectric interface or conductor surface, and B dot AN, the flux density will be 0. So here we have the proof of boundary condition, first boundary condition. As I said before, at the medium 1, Maxwell's equation will hold. In medium 2, the Maxwell's equation will also hold. So we will prove what will be the form of Maxwell's equation at the interface. So I apply the Maxwell's equation on the boundary, meaning that a part of the, as you know, the first Maxwell says the line integral. So line integral of E dot dl. So I take a closed path or a rectangular path. Half of this is penetrate inside medium 1 and half of this is on the in the medium 2, and then apply the boundary conditions. That has half part in medium 1 and other half in the medium 2. So I have to see what will happen if electric signals is traveling from medium 1 to 2. So if you see the red dotted line is showing the electric field coming in medium 1, and the solid red line on the figure shows the electric field in the medium 2. So as you have learned in physics that electric field might bend because of the medium constants, the characteristics of the medium. So I decompose E1 in two parts. One is the normal component that is perpendicular on the interface, and another is the tangential component that is in parallel to the interface. So normal component for E1 is shown in green and the tangential component in blue. So for medium 2, you can see E2N is normal component, E2T is the differential component, tangential component. So now we apply Faraday's law or first Maxwell's equation. So apply substitute them in first equation. So first equation we have so in the Maxwell's equation we have the path we use for Maxwell's equation have four sides. So side AB, so I just expand the Maxwell's equation write the Maxwell's equation for this rectangular path. So you have side AB, electric field, line integral of electric field for side AB, side BC plus side CD and plus side DA, that is equal to the closed path of E dot dl. So I am writing the components of this Maxwell's equation, and right hand side has the time derivative of B dot ds. Now I replace dl. So for AB the length is delta L, for AN length is delta W over 2, for BC half of this BC is delta W over dt, and for that case the electric field is E1N. So for AB the electric field is E1T because it is E1T is in the same direction of AB. So electric field in this direction is E1T, the tangential component. AB is parallel to the boundary. That's why we have to take the parallel component of electric field E1T and times the length is delta L. For BC we have half of this, we have component E1N and other half has the component E2N. So we write E1N delta W over 2 plus E2N delta W over 2 for the electric field for the E dot dl of side BC. Similarly for CD, we see we are moving from C to D. So we have the electric field 2T in the opposite direction. So I write minus E2T and the length is delta L. Similarly for D to A, the electric field is E2N negative delta W over 2 and negative E1N delta W over 2. And right hand side we take the surface B, and surface is the delta L times delta W. So now, as you know, we have to choose the boundary interface. So the idea is the rectangular side, the W, delta W side should be shrinked to get or to lead to bring the area closer to the surface, closer to the interface. So if you go to the closer to the interface, delta W will be approximate to 0. We put delta W equal to 0 in the above expression, and we come up with E1t minus E2t equal to 0. That's equal to tangential component of electric field is equal to the tangential component of magnetic field. So therefore, we usually can tell that the tangential component for electric field in both medium will be same. The tangential component of electric field is continuous. And if we want to write the general form or vector with vector sign, so we know that E1t has a tangential direction, parallel direction AT. So I introduce AT on both sides, and E1t AT is basically is the electric field, total electric field minus the normal component of the electric field. So the tangential component, we can write the total electric field minus the normal component. So similarly, E2t can be written as total electric field minus the tangential normal component of electric field. And then we rearrange them. So write E1 minus E2 and minus E1n minus E2n an. And finally, we take a cross product with normal direction an. So for both terms, so E1 minus E2 cross an, E1n minus E2n an cross an, and an cross an, according to the mathematics, this will be 0. So we find that E1 minus E2 cross an is equal to the 0. So that is the general form for Maxwell's equation in case of electric field at the boundary of two dielectric medium. If the medium has medium constant sigma 1 mu 1 epsilon 1 and medium 2 has sigma 2 mu 2 epsilon 2. So in this slide, I want to show you how you can find the second boundary conditions, like the boundary conditions for electric flux. So we use the Gauss's law, as the integral form of Gauss's law says d dot ds, the surface charge, surface integral of d dot ds along a closed surface is equal to q. So we have to write d1. Now I expand this. So you see, to apply these boundary conditions, I take a cylindrical surface like this, having the cross-sectional area delta S, and part of this cylinder, half of this cylinder is inside medium 1 and other half in the medium 2, and an is the direction from medium 1 to medium 2 is a normal, the an is the normal vector or the perpendicular vector on the interface. And also we decompose the electric flux d1 and d2 into two parts. The tangential part is d1t and d2t respectively, and the normal part is d1n and d2n respectively. So we show the normal part with green color and the tangential part with blue color, and the total field in in the red color. So now if I apply electric flux, we need to have a closed path. So I am choosing the electric flux that is entering to the cylinder. So you see the arrow showing here the electric flux that is entering from medium 1 and the electric flux that is leaving from the top side of the cylinder, and also this electric flux could produce some charges, or we might have some charges on the surface. So if you have charges, free charges available on the flux, so you see a lot of positive plus signs. Let's assume the charges are positive. A lot of plus signs are on the boundary surface. So this plus signs meaning there are a lot of surface charge on the surface. So a part of this plus are also include inside the cylinder. So this plus sign produce some flux. So this flux is the middle arrow indicates the electric flux produced by the surface charge. So now if I apply these boundary conditions for uh, expand this Gauss law for this cylindrical surface. So the electric flux coming from so as you know, the Gauss's law says the electric flux coming out from a surface is equal to the charge enclosed by this. So the electric flux coming entering to the surface is d on n delta s, and leaving is d2n delta s. So these are the difference. So that is, and this difference is contributed by the surface, the charge enclosed by the surface is rho s times the delta s. Now if we drop delta s from the expression, you will get d1n d2n is equal to rho s. Now let us apply the produce the general expression. So I write d1n minus d2n an, also do the dot product with an equal to rho s. So I will say d1n minus d2n dot an equal to rho s. Then d1n can be written on d1 minus d1t at, and d2 is d2 minus d2t at. And then if we expand this or do some rearrange of this expression, you will get d1n d2 d1 minus d2 dot an and d1t minus d2t at dot an. At dot an, they are perpendicular to each other, so that will be 0 equal to rho s. So you get come up d1 minus d2 dot an equal to rho s. So this is the second boundary condition. Let us prove third boundary condition. So now let me draw a surface like this. So this is the boundary interface, and this side is medium 2, this side we have medium 1, and this is the surface here. So let's think the current, the surface current in the direction, this direction. So this is my surface current K, and I take the axis system like this. In this direction we have y-axis, and here we have x-axis, and the z-axis is just the perpendicular of this surface. So z is perpendicular on this surface. I draw the magnetic field diagram here. So let's say this is my interface, and on this just I am drawing interface, translating this interface over there, and the magnetic field that is coming from medium 1, let's say this is the magnetic field, and in medium 2 This is the magnetic field. So H1, let's say H1 has an expression like H1T in the AT direction and H1N in the AN direction. So HAT is this one, H1T. I write in vector, and this is my H1, sorry, this is H1N on 1T. I decompose H2, so this will be H2T and H2N. So H2, but H2T at AT direction plus H2N at AN direction. So I took Amperian path here. Let's say this is my A, path B, and this is C, and this is D. So this is C, D, and this is Maxwell's equation like this. So circulation of H field over the length dl. So this is the length is equal to I current plus d over dt. I can write d over dt at outside, or you can write inside the integration. So if you write inside, then d over dt will be partial d over partial t. But if you write it out, the derivative outside, you can write the full derivative d over dt, and then this is d. Okay, I write the expression Ampere's law like this: A B H dl. So I am taking only the magnitude. So BC HDL plus CD HDL plus DA HDL. So let us write it like I. And right hand side is d over dt. And surface, so I write it like d and ds. So now substitute the value. This will be H1T and dl is delta L plus H1N delta W over 2 plus H2N delta W over 2. So this is my delta W. So half is in medium 1 and other half is in medium 2. And for CD, that will be H2T, that is in the opposite to H2. So H2T delta L minus H2N delta W over 2 minus H delta W delta L. Now I can write it like H1T delta L minus H2T delta L is equal to I. As delta W is very small, so I can write this term equal to 0, because the purpose of taking the line integral at the boundary or interface, meaning that you have to choose the Amperian path so tiny that it only exists at the interface, not inside medium or inside medium 2. So it is just closer to the boundary. So I write it like this. So you can write it like H1T minus H2T equal to I over delta L, and I over delta L is the current per unit meter, so K. So I got the expression like H1T minus H2T equal to K. So as you see here, K is the surface current. If you put current on the deliberately on the boundary surface, you will see the magnetic flux density expression at the boundary is discontinuous, right? H1T is not equal to H2T. So I want to get the generalized expression. X direction, this is my Z direction, this is Y direction. So this is Y, this is Z, and this is X. The magnetic field in medium 2, let's say the medium 2, K surface current is flowing this direction in Y direction. So you see the magnetic field will be in this way, so this way, and in this direction. So the tangential component is along the x-axis, and the normal component in z-axis, the z-axis, and the current in y. So K basically KAY. So K is KAY. H1T is H1T AT, that is equal to H1T AX, and H1N, the 1N vector is equal to H1N, and this one, the AN is in the Z direction. So now I want to write the expression K. So I want to put a vector sign on this equation. So I write K as a vector K.
meaning that k is in the direction of ay. So you have to put like k ay. So I need to introduce ay in the right hand side. So you have to put ay here, and you have to put ay here, right? So you have to multiply the entire equation by ay. There is no ay component in magnetic field term, so I can write ay, as you know, from the vector expression az cross ax is equal to ay. So where az is basically the an direction. So write an cross ax is base at equal to ay. So I write the right hand side, I write ay, and in left hand side I will write an cross at. So for h1 on t, I'll write an cross at. At h2t, I write an cross at. So therefore, I can take an as a common factor and write h1t at minus h2t h1t at h2t at equal to k. At minus h1n. So you can write the h1 minus h1n n. Cross an is 0. N cross an is 0. So this term with cross with this term goes to 0. So you have h1 minus h2 equal to k. So this is the boundary conditions.